Hello and welcome to the next video in my Pre-Algebra review series. Today's video covers Chapter 4, Section 9 of your textbook, entitled Scientific Notation. By the end of this video, you should have a better understanding of writing and evaluating scientific notation and calculating with scientific notation. Please leave a like if you find this video to be helpful. Give your classmates a heads up too. It'll more than likely help them and certainly help this channel get seen by more students. If you would like me to cover any of these topics in greater detail, please leave a comment in the comment section below. I read them and do my best to answer each as time permits. Please subscribe to my channel and ring the bell icon to be notified every time I release a new video. Thank you. In this slide, writing and evaluating scientific notation, they'd like us to look at numbers in scientific notation, and when they're showing us the answers, what the standard form answer would be. What steps? They want to know which steps are we going to go through to convert the one to the other. What does it look like? Well, let's start with the first one. What they're saying here is to take the number 5. So we got 5, and we're going to multiply that times 10 to the 4th power. Well, what is 10 to the 4th power? It's times 10 times 10 times 10 times 10. And so 10 times 10 is 100. 100 times 10 is 1,000. And 1,000 times 10 is 10,000. So 5 times 10,000 is equal to 50,000. Let's do the next one. They're all going to just go in order here, so they're going to be pretty easy. So in this one, we've got 5 times 10 times 10 times 10. See, they're telling us. And you know exponents. We've already studied these and looked at them. So this is the base number is 10, and it says multiply 10 by 10 by 10 3 times. And here we have it, 5 times 10 times 10 times 10. Or you could say 5, 50, 100, 1,000. So here it is, 5,000 is the answer to this one. And it was written with 3 tens. And here's 5 times 10 times 10. 5 times 10 squared is 500. 5 times 10 is 5 times 10 to the 1st power. Anything to the 1st power is just itself, is the base number. 5 times 10 is equal to 50. There it is. Then here's a special one. 5 times 10 to the 0. And what is 10 to the 0? Well, 4 tens, 3. Look at it. We had 0, 0, 0, zeros. Finally, no zeros. So it's times 1. 5 times 1 is 5. Now we're going to go with fractions, so to speak. We're going to be moving the exponent to the denominator. So here we have 5 times 1 over 10 is equal to 0.5. You take the 5 and you divide, and this is 5 divided by 10 is 0.5. The next one, 5 times 1/10 times 1/10 is equal to 5. Well, it's divided by 100. Well, 5 divided by 100 is equal to 0.05. And then if you do this, it's 5 times 1 over 10 times 1 over 10 times 1 over 10 is equal to 1 over 1,000. 5 times 1 over 1,000, and that's 0.005. That's 5 thousandths. 5 divided by 1,000 is 5 thousandths. 5 thousandths. And now we'll do it. The longest one here is 5 times 0.10 times 1 over 10 times 1 over 10 times 1 over 10 is equal to 5 divided by 10,000. And that is 0.00005. Okay? Writing and evaluating scientific notation. Describe any related patterns you saw in that chart. Well, we saw that as the exponent increases by 10, then the number of zeros increases by 1. We saw that the higher the number 10 was, the more zeros we had added to the back of the number. We learned that 10 to the fourth power means of 1 with 4 zeros behind it. Yeah, it's 10 times 10 times 10 times 10. 1 with 4 zeros, it's 10,000. And 10 squared means 1 with 2 zeros. So we learned that. How about for 3? Based on the patterns you see, simplify 5 times 10 to the 7th. So what is 5 times 10 to the 7th? So what did we do here to simplify it and get this number here? So we took, if you look at it from just the number point of view, we had 5 times 1 with 7 zeros. 1, so look at the 7 zeros. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7 zeros. 5 with 7 zeros. 5 with 7 zeros is 50,000. 50 million, rather, excuse me. Let's do this one. 5 times 10 to the minus 6. Well, in this case, we have 5. We have to move the decimal point in the leftward direction. And when the exponent is positive, we're moving the decimal point in the right direction, to the right. And when it's negative, we're moving the decimal point. Well, what's happening is we're moving it. We're making the number smaller. I guess you can't say you're moving the decimal point right or left. Here we took and we actually added zeros. Here we're like adding zeros to the top of the number. So here we're starting here at the top at the 5, and we're going to move 6 times. So it'll be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5 to below the 6. See, that's where we started at the 5. We're going to the left. 1, 2, 3, 4, 5, 6. 6 loops. That's how many loops we made. So that's as we're going back and forth. We start with the 5 and we take the zeros out to the left. Here, on the positive exponent, we're taking the zeros out to the right. Scientific notation provides a way to write numbers using powers of 10. A number written in scientific notation is the product of 2 factors. The first factor that we're looking at, so here's a very large number. I think it's 7,500,000,000,000, I think is what that number comes out to. So the first factor is greater than or equal to 0, but less than 10. So it's greater than or equal to 1. I think I said 0, sorry. Greater than or equal to 1 and less than 10. And 7 is greater than 1 and it is less than 10. And the second factor is times 10 to how many, to which power. So there's the 2 factors. So the scientific notation lets you know the size of the number without having to count the digits. For example, if the exponent of the 10 is 6, the number is in the millions because it has 6 zeros. It's kind of straightforward. If the exponent is a 9, then the number's in the billions. So that's kind of convenient. I have a little real world example here. About 4,200,000 people visit the Statue of Liberty each year. Write the number in scientific notation. So we start off by taking 4,200,000. Okay, and we move the decimal place till we get the decimal place, which is right here, is where the decimal place is. We've got to get it all the way over here till it's just before the last non-zero number in the statement. So you go 1, 2, 3, 4, 5, 6. So the numbers. So now we've moved it 6 times. So now the decimal point is right here below the 4 and above the 2. The decimal point is right here between these two, right here. It's because we moved it 6 times. So now it's 4.2 is the first number after, and then also there's a bunch of zeros after. You drop any zeros, you can drop them all. Anything below the last real number that's above 0. So it could, if there's a 2 or a 3 or a 5 or whatever, you can't erase the zeros ahead of that. You have to only erase the zeros in the backside. So then we end up with 4.2 times 10 to the 6th. That's the answer in scientific notation. So now they want us to check our understanding. They'd like us to write these numbers in scientific notation. Well, the first one here, 54, 500,000. And the decimal point is right there. So now, in order to get to this, we have to go all the way over to below the 5 and above the 4. That's because that's the last digit, greater than or equal to 0, but less than 10. Now, how far did we have to move the decimal place? 1, 2, 3, 4, 5, 6, 7 times. So the answer here is 5 point, because we moved the decimal place, 4, 5, because that's the next real numbers. We're going to drop the zeros, times 10, times 10 to the 7th power. Okay, let's do this one. 723,000. The decimal point is right there. We're going to move it 1, 2, 3, 4, 5 times to get below the very last non-zero number. So we're right here is where we're moving the decimal place. So now we're going to have 7.23. We're not going to lose those. We're going to lose these zeros here. We're going to get over to those. And then it's times 10 to how many times do we move it? We move 1, 2, 3, 4, 5 times. 10 to the 5th. Last one here. We have 602, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0. 0, 0, 0, 0. Yep, 3 sets of zeros. The decimal point is right here. So we've got to get it all the way down to here. How do we do it? We do 3, 6, 9, 10, 11. So the answer is 6.02. Get rid of all the zeros that are below the last real non-zero number. And then it's times 10 to the 11th power. Okay? Write in scientific notation. In scientific notation, you use the negative exponent to write numbers between 0 and 1. So if you're trying to write 0.9 as your number, how do you can use scientific notation, or in this case it says 0.000079 that they want us to do. It means we're going to have to have a negative exponent. So here's the number they want us to use, which is right here. And so I'll draw it out like I did before. So it's 0.000123079. So this is the number. The decimal point's way up here. Here's the decimal point. They want us to move it down to this spot right here so that you have one non-zero number less than 10 and greater than or equal to 1 between the first two digits here. So what do we have to do to get it? We have to go -1, -2, -3, -4, -5. So the answer then happens to be 7.9 times 10 to the -5. Okay? Check our understanding. Let's do a few of these ourselves. So up here we have 0.00021. We're up here with the decimal point, and we want it right here, right below the first real number. Okay? And to get that, we have to move the decimal place -1, -2, -3, -4. So the answer is 2.1 times 10 to the -4. moving over here. We have 0 0.123, see 1, 2, 3, 4, 5, 6, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 7, 5. So we're up here with the decimal point, and we want the decimal point. Where do we want it? We want it right here. And if we could put the decimal, we could put a 0 there if we want. So how do we get it there? So we have 5 times 10 to the how many places? 1, 2, 3, 4, 5, 6, 7, 8 to the minus 8. Okay, and now this one down here, it's way long. So we got, what do we have? 1, 2, I'm going to put a little marker. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So is that it? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, 10, 11. So we have 0 0.123, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and we're here. It is 1, 2. So it's 1, 8, 0, 3. So they want us to move it, or we have to get it into scientific notation. So that means we're going to move to the negative. We're going to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the answer is 8.03 times 10 to the minus 11. Okay, example 3. We're going to write in standard notation. So this time we're going from scientific notation to standard notation. And what we do is the number is 8.9 times 10 to the 5th. Well, you can take the 8.9 and move it 1, 2, 3, 4, 5 times to the right. Because now we're increasing, we're multiplying by a large number, so we're increasing the size of the number. So it goes from 8.9 times 10 to the 5th to 890,000. You see, so now we're making the number larger. Here, let's look at the next one. 2.71 times 10 to the negative 6. So here the decimal point is way down here. And now we're going to have to move it to the left. So it's 1, 2, 3, 4, 5, 6 times. That's how far we had to move the decimal point from here to here because of the scientific notation. So we moved it this way with a negative. We moved it this way with the positive. We had added zeros. We're adding zeros. We're like subtracting some tens. Okay? Or dividing out tens and going the other way. Okay, example 3, check your understanding. So they want us to write each number in standard notation. So 3.21 times 10 to the 7th. 3.21 times 10 to the 7th means that they want us to do what? They want us to increase the number. So right now it's 3.2. We're going to end up with a big number. So how do we do that? We're going to have seven zeros in essence. But we already have a couple spaces filled here at the 2 and the 1. So we're going to say 1, 2, 3, 4, 5, 6, 7. Going back, we're going to get rid of this. So it'll be a comma there, 1, 2, and a comma here. So it's 3, 2, comma 1, 0, 0, comma 0, 0, 0. 32,100,000. Let's try this one. This one's going to be a very small number. We're going to have a decimal point with a bunch of zeros in the beginning. Because of this 0.59, we're going to start over here, 5.9. And we're going to be adding zeros this way. And to do it, we're going to do, you take this number, since we have to jump around the 5, we're going to lower this by 1. This 8 will become 7 in our counting. But so it's 1 or 8, 7, 6. We could do that. How about 8, 7, 6, 5, 4, 3, 2, and 1. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. Put the decimal point right here and put a 0 in front of it because you've got the decimal point. So this one's gone. So it's going to be 0.000, that's those 3 zeros, 0, 0, 0, these 3 zeros, and 0, 5, 9. Okay? And now we're going to do this one here in C. So we have 1, we're getting large. So we're going to have 1.006 times 10 to the 10th. So we're going to add from here 10 equivalent of 10 spaces and fill the empty spaces with zeros. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we count our commas coming back. 1, 2, 3, 1, 2, 3, 1, 2, 3. There's a 10. So we're going to have a 1, 0, comma, 0, 6, 0. Now we got zeros and 6. 0, 0, 0, comma, 0, 0, 0. Rewritten out. And this ends up being 10 billion, 60 million is the answer on this one. Okay, in example 4, changing to scientific notation, we're gonna look at 2 problems. And before we get started, it says for a number to be in scientific notation, the first digit must be greater than or equal to 1 and less than 10. So in essence, what it means is we're going to take and we have to move the decimal point to the point where there's one number to the left of it and all the rest are to the right of the decimal point. So in problem A, we have 0.37 times 10 to the 10th. Well, in order to convert this, see, it looks like scientific notation, but it's not in scientific notation because we don't have the decimal point in the correct spot. In this case, it'd be between the 3 and the 7. So we have to do that. So in the example here, we're taking, here's the problem, 3.37. And what we want to do is we want to move the decimal point to right here to the 3.7. Well, it shows you here that we're going to multiply this piece, the 0.37 times 10 to something, because we have to get this number from this number. So I guess you have to ask yourself, well, here's where I want to be, and what do I have to do to that number? Multiply by 10 or divide by 10 or whatever the number might be to get it to this number, to get it to the original number. So what do I have to do to the new number to get it to the original number? Well, it's kind of easy. You say to get from 3.7 to 0.37, you have to divide it by 10. And so 3.7 divided by 10 is equal to 0.37. So this divide by 10 right here is really what? It's 1 over 10. And we also know that from an earlier slide that 1 over 10 is the same as 10 to the minus 1. Right? We know that. So up here, we've got 3.7 is where we want to be. We came from 0.37. In order to get there, we had to divide by 10. And that's 10 to the minus 1, as I showed you down here. And then you multiply the entire thing by 10 to the 10th. Well, we also know from a previous slide that if your base numbers are the same, 10 to the something and 10 to the something, you add the exponents when you're multiplying. We're multiplying, so you add the exponents. And adding the exponents will give us 10 to the minus 1 times 10 to the 10th, or 10 to the minus 1 plus 10 is equal to the 10 to the 9th. So 3.7 times 10 to the 9th. Let's do the same thing down here for B. It's 453.1 times 10 to the something, I'm going to leave it open, I'll leave a little circle up here, times 10 to the 8th. We already know that one. So what we're looking for is what's in this circle. What's in the circle right there. So how do we, in order to get, what we want now is we want 0.4531 times 10 to the something times 10 to the 8th. Okay, that's what we're looking for. So how did we get, here's where we are, and here's where we want to be. So we want to be here. What did we have to do to this number to get this? Oh, well, this is 450. This is 4.5, so we have to multiply by 100. So that would be 4 times 10 squared times 10 to the 8th is equal to, as we show up here, 4.53. Anyways, it's 4.531 times 10 to the what? To the 2, because it's squared, to the 10th, because we have 2 here, and that adds with the 8. So it's 10 times 10, 2 plus 8 is equal to 10 to the 10th. Okay, that's kind of what it shows here. 4.531 times 10 squared times 10 to the 8th, and you add this exponent, and you get that exponent. Okay? So now it says write each number in scientific notation. We're going to check our understanding here. So let's try it. So we're at 16 times 10 to the 5th, and we want to be at 1.6 times 10 to the something times 10 to the 5th. So what does that have to be here to move this? So we are at 16 and we want 0.16. What do we have to do from 0.16 to get to 16? We have to multiply by 10. Well, multiplying by 10 in this case is just sync a 1. So it's 1.6 times 10 to the 1st times 10 to the 5th, and that equals 1.6 times 10 to the 1 plus 5 is equal to 1.6 times 10 to the 6th. Let's try this one. We have 0.203 times 10 to the 6th. And what we're going to do is we're going to change this, and it's going to be, we're moving this 1 decimal place. So it's going to be 2.03 times 10 to the something times 10 to the 6th power. And in order to get from 0.203 to 2.03, all we had to do, to get from 2.03 to 0.03 is we have to divide by 10. To divide by 10 means we're going to have a negative 1 right there in that little circle. So it's going to be 2.03 times 10 to the negative 1 times 10 to the 6th. And now it's 2.03 times 10 to the minus 1 plus 6 is equal to 2.03 times 10 to the 5th power. Let's do this one over here. C. So we have 7, 7,243 times 10 to the 12th. So now we're going to convert this number to scientific notation. Just the number part, not the power, right? So we got to want 7.243 times 10 to the something times 10 to the 12th. So what do we have to do to this number to make 7.243 to make it look 7,243? Well, we have to move the decimal point 1, 2, 3 times. So that means multiply by 1,000, 3 to the 10th. So 7.243 times 10 to the 3 plus 12 is equal to 7.243 times 10 to the 15th power. Comparing and ordering numbers. You can compare and order numbers in scientific notation. It makes it kind of easy. So how can you do that? Well, take these numbers here. 0.064 times 10 to the 8th, 312 times 10 to the 10th, 10 to squared rather, excuse me, and 0.58 times 10 to the 7th, and order them from least to greatest. So first of all, you write each number in scientific notation. So we take the 0.064 and write it as it is 64 to 6.4 times 10 to the 6th. And we knew how we did that. How do we do it? We took the number we want to be is the 64. We want it to be 64. And in order to get to this point, we had to divide by 100. We had to move the decimal point 2 places to the left, divide by 100, and that's 10 to the minus 2. So you take 10 to the 8th plus 10 plus minus 2 gives you 10 to the 6th. That's how we got this one. This is the same way we wanted this. In order to get here, we have to multiply by 2. So 10 times 2 plus 2 is 10 to the 4th. And again here, we're at 0.58. We want to be 5.8. That means we have to, this number is where we want to be. To get here, we got to divide by 10 to get to this number. So we started with a 7 here, and we subtracted 1 because we did a divide by 10. Subtract 1. So that's the numbers converted. Now that they're converted, first of all, you look at what is the smallest power of 10 you have? Well, the smallest power of 10 we have is the 3.12 times 10 to the 4th. So are there any other 10? No. So this is the far lowest, the least value, which is, I see there's a little bug here, but oh no, they converted it back. So we put the minus 4, the 0.4 here. Then we had 2 raised to the power 6. Well, then what you have to do is you have to look and say, well, is this one the smallest one, or is this the smallest value? And now it's easy to see that 5.8 is smaller than 6.4. So the 5.8 is in the middle, is the second one up, and then the greatest number is 6.4 times 10 to the 6th. And now you convert them back to go from 3.12 times 10 to the 4th to 312 times 10 squared is where you're going back with. 312 times 10 squared right here is where you're going back to. You're just converting it. You don't have to even do the conversion. You just find it and go back, actually. But then it's the 0.58 times 10 to the 7th. 0.58, 10 to the 7th is that one. And then over here, we got 0.064 coming from here. So that means we're 0.064, 10 to the 8th. And if you look over here, it's the one you started with. We're going to check our understanding. It's the same problem we're doing. I've done all the work. We're just going to talk about it. So here's the 3 numbers they give us. 526, 10 to the 7th, 18.3, 10 to the 6th, and 0.098 times 10 to the 9th. So we do the conversion. We take 5.26 here. To get to this, you have to multiply times 100. There's the 100 and the 7. So 2 plus 7 is 9. So there's this number. We did the same thing here. We went from 18.3 to 1.83. Means we have to multiply by 10 to get from where we are to where we were, or we want to be to where we were. So we get that number here. We add the 2 together. We get 7. 1 and 6 is 7. Over here, 0.098. We want to be 9.8. So in order to get from 9.8 to 0.98, 0.098, we have to divide by 100, or it's 10 to the minus 2. So minus 2 plus 9 is equal to 7. So it's 9.8 times 10 to the 7th. Then with given that information, you can find out which one's the smallest. Well, the smallest is which one? These are the 10s, the 7ths are the same. The 1.8 is smaller than 9.8. So the smallest is 1.8 times 10 to the 7th, and here it is. The 1.8 times 10 to the 7th was from here where we started, 18.3 times 10 to the 6th. And then this one here is the next one in order, the 0.9. Here, when we did it from here, they were both 0.7s, but 8.9, 10 to the 7th is really smaller than this one. So we put him down here because here's the number. And 5.26 times 10 to the 7th is this one way over here, which started off 5.26 squared here gives us the 9. We take it back to the 7. We're back in place. We did the same thing down here. We took the numbers. I colored them so you know where they ended up going. We convert them. 8, we want 8. We want to remain it at 8. So it's times 10 to the 1. 8 times 1 times 10 to the minus 9. So again, nothing changes here. This one here, we converted it from 14.7 to 1.47. So that means we had to multiply the new number by 10 to get to this, to the 14. And then we add the exponents, and we end up coming up with, oh, I see a bug in here. I see a bug in here. This problem here is minus, and then you take this and minus 7. This should be minus 6 right here. Sorry. Minus 6. But we can live with it. And here's a 20.22. We want it as 2.2. And then in order to get from 2.2 to 0.22, we have to divide by 10. So 2.2, we take the 10 to minus 1. Minus 10 is minus 11. So these are all in order now. The smallest number is to the 11th. This one here, the yellow one. So it's 2.2 times 10 to the minus 10. And then the next one, the next greater one, is the blue one, which is this one here, which is the minus 9. And then minus 11 way over here is the largest. The minus 7 is the largest number. So smallest, next, and then largest. There, follow the order here. So hopefully that's clear. But so all we did is once we found the order, we just went back and got the number that whichever, this one went here, this one went here, this one went here, and you can see where I moved them around by the colors. So you can multiply numbers in scientific notation by using the rule for multiplying powers with the same base. So let's take a look at it. So let's multiply with scientific notation. So 3 times 10 to the minus 7 times 9 times 10 to the third. Well, here's the two problems are multiplied right here. There's where we're multiplying them. So what is it really? It's the 3 from here is the 3 here. And times 9, well, we jumped over here because multiplication you can do in any order you want. So we grab the 9 right out of here, put the 9 here, and then we've got the times 10 to the minus 7. Here's 10 to the minus 7 right here, and here's 10 to the third right here. So we put them in our own order. So we got 3 times 9 is 27, and then 10 to the minus 7 times 10 cubed. You add the exponents, so it's minus 7 plus 3 is minus 4. So it's 27 times 10 to the minus 4. And then to write it in scientific notation, we 2.7 times 10 to the first, because I had to go from 27 to point, this is where we're ending up. So that means we have to multiply this number to get 27. So we're multiplying times 10, 10 to the first. Okay, and then we have the number minus times 10 to the minus 4, And then to get done with this, it's 2.7 times 10 to the minus 3, because it's 10 to the 1 minus 4, which is minus 3. We'll do it again. Let's check our understanding. So we're going to take I've done them for you basically here, but I'll do it again. So it's 4 times 6 times 10 to the 4th times 10 to the 6th. So then 6 times 4 is 24 times 10 to the 4 plus 6 is equal to 24 times 10 to the 10th. And now we're going to write this in scientific notation. So we wanted to get to 2.4 times 10 to something times 10 to the 10th. Okay? And to get from 0.24 to 24, you have to multiply by 10. So it's a 10 to the first power. So it's 2.4 times 10 to the 1 plus 10. And that equals 2.4 times 10 to the 11th power. Let's do this one. 7.1 times 8 times 10 to the minus 8 times 10 to the 4th. Okay, what is that? 7 7.1 times 8 is what, 56, and what do we have to add? 7.1, and 0.1 times 8 is 0.8, so it's 56.8 times 10 to the minus 8 plus 4. Okay, those come out pretty easy. So it's 56.8 times 10 to the minus 4. And now we have to convert this to scientific notation. So, like I said before, you take go where you want to be. You want to be at 5.68. We wanted this decimal point to be here. Well, now that we have it like this, what do we have to do to this to make it look like this? We have to multiply 5.68 times 10 to get to 56.8. So it's times 10 to the first power times 10 to the minus 4. And what carry it out is 5.68 times 10 to the 1 minus 4 is equal to 5.68 times 10 to the minus 3. Okay? Here's a real world problem. It says the Great Pyramid of Giza in Egypt contains about 2.3 times 10 to the 6 blocks of stone. 2 million some stones, right? 2.3 million stones. On average, each stone weighs 5 times 10 to the 3rd pounds, it says. Or pounds. So it says, about how many pounds of stones does the Great Pyramid contain? So let's do it. We'll do it out. We've got the answer here, but let's work it out ourselves. So we've got a 2.3, and we have a times 5 times 10 to the 6th times 10 cubed. I changed the dots for the multiply. It comes out a little easier. So what is 2.3 times 5? Well, that's a good one. That's going to be 2 times 5 is 10, and 0.3 times 5 is what? I don't know. 11.5. So 11.5 I cheated. I went up and looked at my answer. 11.5 times 10 to the 6th plus 3. So it's 11.5 times 10 to the 9th. Okay, but can we leave it at 11.5 times 10 to the 9th? No, we have to get it in scientific notation. So we want it to be 1.15 times 10 to the something times 10 to the 9th. So in order to get from 0.115 to 11.5, we have to multiply this number by 10 to get where we used to be from where we are now. So that we're going to multiply by 10 means 10 goes right here, gets a 1, 10 to the first power. So 1.15 times 10 to the 1 plus 9 is 10. So the answer is 1.15 times 10 to the 10th pounds. And I'll write pounds in here. Pounds, pounds. Okay, a chemistry problem for us. A hydrogen atom has a mass of 1.67 times 10 to the negative 27 kilograms. Okay, what is the mass of 6 times 10 to the third atoms? So that's 6,000 atoms, each weighing 1.67 times 10 to the negative 27 kilograms. And they want us to express the resulting scientific notation. Okay, so here's all the solution is all written here, let's do it by hand a little bit. Let's check it out on our own. Okay, so we're going to write this out. We're going to say that 1.67, and we got this, and that times 6 times 10 to the negative 27 kilograms times 10 cubed. So 1.67 times 10 to the 6th is 10.02. Those I multiplied these two. And then it's times 10 to the minus 27 plus 3, which is 10.02 times 10 here. 10 to the 27 minus times 10 to the minus 24. Minus 27 plus 3 is minus 24. Okay, so now we have to write this in scientific notation. So in order to, here's what we want to be is 1.002 times 10 to something times 10 to the minus 24. So what does this something here have? What does that something right there have to be? Well, in order to get from where we want to be here, 1.002 to 10.02 means that we have to what? We have to multiply this times 10. So we're going to multiply it times 10. Okay? So now we're at 1.002 times 10 to the 1 minus 24. And so that's 1.002 times 10 to the minus 23 kilograms, kgs. And it comes out right.